I'm Dan Roos. I'm a member of the committee for the Charles L. Miller Memorial, and I would like, on behalf of the committee, to welcome you all today. We have a terrific turnout, and I'd like to just spend a few moments giving you a little bit of background about Charlie Miller before I have the pleasure of introducing our speaker for the day. Charlie was department head of the Civil Engineering Department from 1962 to 1969. And just to give you an appreciation for what Charlie went through, in 1962, when there was a search for the department head in civil engineering, the job was offered to two people on the outside, both of whom turned it down. The department was really in terrible shape. There were very few students. The research agenda was not deemed to be of MIT quality, and there was serious consideration about shutting the department down. The Dean of Engineering at that time was Gordon Brown, who I'm sure many of you have heard of, who was a very dynamic individual. And as a last ditch, they decided to offer the job to Charlie. Bear in mind, Charlie was 32 years old. He was an associate professor, and he did not have a PhD, okay? This is not exactly the profile for your typical department head in the School of Engineering. And Gordon Brown said to him, "You've got 5 years. Either you turn this department around, or else we're going to shut it down at the end of 5 years." And he not only turned it around, but really dramatically had an impact on the entire profession and the School of Engineering. And he had that impact because he decided to focus on two things. He decided to focus on computers, and he decided to focus on systems. Now, in the 1960s, computers were really just coming into major use at MIT, and they were viewed primarily in terms of substitution for a lot of computation. And the electrical engineering department was starting to offer courses that were geared towards computer professionals. And Miller had two impacts. He said, first, this is more than a computational device. This is something that allows one to do engineering problem solving. And therefore, we need to develop mechanisms for man-machine communication to make it easier for engineers to communicate with the computer. And secondly, our educational courses should not be just for programmers. They should be for engineers who want to understand what the impact of these devices are. And so he really had a significant impact in several ways. First, the development of Course 100 in civil engineering, which turned out to be the largest undergraduate computer course at MIT. Secondly, Charlie had a number of computers implemented. I won't go through the whole list, but he wound up with a System 360 computer, which, aside from the MIT Computation Center, was the largest computer on the MIT campus. And he focused on developing a series of research programs, the largest of which was one called the Integrated Computer Engineering System, ICES, which really revolutionized problem solving in the civil engineering field. And believe it or not, that system is still in use today. From a systems point of view, Miller said, you know, we shouldn't only be doing highways, we should be doing transportation systems. And we shouldn't only be doing structures, we ought to be doing construction and building systems. And we shouldn't only be doing fluid dynamics, we ought to be doing water resources. And he really laid the groundwork for systems thinking at MIT in terms of what we're calling now sociotechnical systems. So we felt it was only appropriate, given the impact that he had, that he should be memorialized. And so we have set up this yearly lecture series in his honor. It's really my great honor to introduce our speaker for today, Joe Sussman. Joe has had an incredible impact both within and outside MIT, and let me just briefly describe some of the activities that he's been involved with. From an MIT point of view, he joined the faculty in 1967 in what was then the Department of Civil Engineering, of course now Civil and Environmental Engineering. From 1977 to 79, he served as Associate Dean of Engineering for Education. From 80 to 85, he was the department head in civil engineering. From 1986 to 1991, the director of the Center for Transportation Studies. And from September of this year through now, he has served as the interim director of the Engineering Systems Division. So he certainly has made enormous contributions in terms of academic leadership at MIT. His research spans a very wide spectrum. I mentioned before ICES. Joe was very instrumental as part of a group that several of us were involved with called the ICES Architecture Group, which was concerned with the design of the system. And his particular specialty was developing a system for dynamic memory allocation, given the fact that at that point in time, computers had a finite amount of memory, and this was a way of greatly expanding the capacity that an engineer had direct access for. He has focused primarily in the transportation field, and in particular in the field that was originally called Intelligent Vehicle Highway Systems, and more recently, Intelligent Transportation Systems. In 1991, he was appointed as the first Distinguished University Scholar by IVHS America. And in that capacity, he served with a group of people that developed the original strategic plan for intelligent vehicle highway systems. He has had any number of important positions, including being on the ITS America board from 1991 to 1998 and serving on the executive, as chair of the executive committee in 1994. He's been on the ITS Massachusetts board. Recently, he was appointed by US DOT to head its ITS advisory board. And he has conducted extensive research in ITS all over the world, not only here in the United States, but in Mexico, Malaysia, Portugal, to name a few other places. In parallel with this, his focus has been on rail transportation, and in fact, he has been for many years the J.R. East Professor, and this was a chair given by the East Japan Railway Company. His focus has been on service reliability and operations, and I noticed Carl Martland was here today, who has been one of Joe's close colleagues working in the rail area. He has chaired many committees for the Transportation Research Board in the rail area, and also chaired a committee for US DOT, basically looking at what research and development should be in the Federal Railway Administration. More recently, he has been focusing on what he describes, and I hope I get this right, as complex, large-scale, interconnected, open, socio-technical systems, CLEOS. And to a large extent, that's going to be the subject of today's talk, and so I won't go into any further discussion of that. From a teaching point of view, he has started numerous courses. 1997, he got the Civil and Environmental Engineering Effective Teaching Award. In 2002, the Technology and Policy Program awarded him a Faculty Appreciation Award for starting a new course, Introduction to Technology and Policy. He has had 2 books. In 2000, Introduction to Transportation Systems, which has been translated to Greek, Spanish, and Chinese. Another book in 2005. From a service point of view, he has advised transportation programs at Northwestern, Toronto, Cornell, Michigan. As I said before, he has headed many committees for the Transportation Research Board. I won't mention them all. But let me conclude by just mentioning a few of the awards he's received. In 2001, he received the Roy W. Crum Distinguished Service Award from the Transportation Research Board, which is the most distinguished award that TRB gives. In 2003, the Council of University Transportation Centers awarded Joe for distinguished contributions to university education and research. 2002, ITS Massachusetts established the Joseph M. Sussman Leadership Award. 2007, he became a Fellow of the American Association of the Advancement of Science. And in 2008, the engineering school alumni of CCNY, which was City College of New York, which was his undergraduate alma mater, gave him a Career Achievement Award. So he's really a man of all seasons who has done just a variety of things. Before I ask him to come up, I noticed there are some people in the back. Why don't you come in? And I think there might be some extra chairs in the next room which you can grab. So at this point, it really is my distinct pleasure to introduce Joe Sussman.
Dan, thanks so much for that excellent introduction. You know, all the faculty have these one-pagers that they give out when they're going to give a speech to give the Master of Ceremonies something to go on. Dan's the first one who actually read the whole thing and presented it to him, leaving me with only a moderate amount of time to actually speak. Dan has been a mentor to me from my earliest days of MIT, and we talk fondly about those days in the 1960s when we were both graduate students. Dan then joined the faculty. I joined several years later, and those years with Charlie Miller were really something exceptional. So it's an honor for me to give a talk in the context of this lecture series, because Miller had as profound an impact as you could imagine on the careers of many, and certainly me. Let me acknowledge that we have here in the front row the Engineering Systems Division Alumni Advisory Council sitting in a solid phalanx right before me in the first row. I think they're there in case people rush the stage. They'll have a chance to buffer me. So let me try and get into this with some sense of where I come from and my perspectives on systems and how they built. I think my first real exposure to systems was a class that I took, a graduate class in 1985. It was 116J. It had a joint number with many other departments in the School of Engineering. And it was a large-scale systems class with about 50 graduate students broken up into groups of 5 that worked on particular components of the system in question for that semester, and then worked together to merge it. And I really got a terrific exposure at that very early stage to systems at at MIT and how we think about it. It's on the research side, my first look at systems and getting a sense of what one had to do to really get one's arms around the system and make effective change was working with Professor A. Sheffer Lang, who was a senior faculty member in those days, and he had attracted some funding in rail and asked me as a junior faculty member to participate, and I decided that would be a good idea. And we did some very interesting analysis of rail service reliability and what one could do to make freight railroads in the United States run more reliably. And we had a pretty compelling story, I thought. And I said to Chev, I think it's time to go out and tell our story to the railroad industry and to try to affect some change. And he said, well, we'll give it a try. We'll see what the industry thinks. I thought we were just going to throw our glove out on the field and everyone was going to say, isn't this wonderful? Let's implement the MIT methods. I was a bit naive, of course, getting around the socio-technical aspects of an industry, in this case railroads, that had been around for 100 years, and convincing them that there's a new way to do it turned out to be rather non-trivial. So it took a while, but we did have an implementation, but it wasn't simply a question of coming up with some good ideas. The same sort of thing in the ITS area, which Dan mentioned, the notion of using advanced technologies to control highway systems and to create more effective public transportation systems seemed on its face to be an obvious thing to do, but to get people to actually implement this within the context of a conservative industry, think the Massachusetts Department of Transportation, was difficult indeed. So nowadays I'm doing a lot of work on high-speed rail and the idea of high-speed rail as a potential regional development impetus. And again, we're recognizing the issues are not the technology issues. The issues are the socio-technical issues. You've got to get the technology right, but there's much more to it than that. So we actually have a project now on high-speed rail in the Northeast Corridor. And it's worth pointing out that graduate experience I had back in 1965 when I took 116J was high-speed rail in the Northeast Corridor. So I am nothing if not tenacious. I've been working at this for many years, making fairly moderate advances. Okay, so we're talking about complexity. We're talking about complex systems. Lawrence Peter, who is well known for having written the Peter Principle, people getting promoted to their highest level of incompetence and then stopping, clogging up the system, famously said, some problems are so complex you have to be highly intelligent and well-informed just to be undecided about them. So I think many of the ones that we talk about are in that category. So today I'm going to link together two concepts. I'm going to link together the concept of critical contemporary issues, CCIs as I often call them, and complex socio-technical systems. The title of the talk is making a case for complex socio-technical systems, but one has to begin by linking together these notions. So if one is talking about critical contemporary issues, you can all have your own list, I am sure, and this is incomplete, of course, but there are a variety of issues that we face that are of very expensive, very affecting of the human condition on this planet. They are things like global climate change, energy and the environment, developing country megacities, the global economy, and so on and so forth. One could, as I say, go on. National security is another. And as one looks even at this short list, one recognizes that these are hardly disconnected. That if one looks at energy and the environment One obviously ties it, for example, on the bottom line to mobility and how we are going to create an energy system that allows us to retain mobility without having profound effects on the environment. So these things all interlink with each other. And it was very articulately put by President Johnson's wife, Lady Bird Johnson, who, to quote her obituary in The Economist back about 5 years ago, found that in dealing with highway beautification, which was her thing when she was First Lady, it was like, quote, picking up a tangled skein of wool, all the threads are interwoven. Recreation, pollution, mental health, crime, the crime rate, rapid transit, war on poverty, parks, everything leads to something else. And I think that was a very insightful perspective that Mrs. Johnson had. And it relates to the fact that we've got these highly interlinked and hence complex issues that we deal with. So now let's turn to complex socio-technical systems, which is, of course, directly linked to critical contemporary issues. Almost all of them, virtually all of them, I would argue, have a complex socio-technical system at its core. So we need to understand, if we're going to deal with these complex, critical contemporary issues, we're going to need to understand complex socio-technical systems and how we can use that as a framework to study these questions we're so concerned about. So let's parse this relatively briefly, I hope. I'm not going to spend time on systems. Everybody here has their own formal or informal definition, the idea of having interconnected components and subsystems. Often they are structured hierarchically. Usually in the systems we're interested in, they interact with their environment. They provide input to the environment and receive input from the environment. They're often stochastic. They're often nonlinear. Feedback is critical. All the kinds of things that you're aware of in the context of understanding what a system is. Sociotechnical, again, a relatively intuitive definition. We have systems that contain important technology subsystems and components that in fact help control, are central to its performance. They are not incidental. And they have societal, political, and economic relevance and impact. That is, they are connected quite directly to the social sphere within which we operate. Many of you heard me talk about various kinds of complexity, and many of you know I wrote a paper entitled 20 Views of Complexity, and I hasten to say I'm not going to list all 20, but there are several that are of some particular interest in the context of this talk. People here will understand structural complexity, the systems with large numbers of components and subsystems that interconnect. Behavioral complexity makes their performance very difficult to predict. But two you may not have heard of. One is evaluative complexity, which reflects the fact that in a socio-technical context, you have many different points of view about what good performance actually means. Different stakeholders will have very different perspectives on what good performance means. Me living out in the suburbs of Boston is thrilled by the idea of an additional runway at Logan International Airport to improve my quality of service, where some guy living in East Boston with 747s flying within 100 feet of his house all day long may have a very different view about whether that makes sense, and hence evaluative complexity. And finally, nested complexity, the notion that we have a system with a complex physical domain, but surrounded by what I call a complex institutional sphere, which has the organizations and stakeholders embedded on it. And graphically, the idea here is there's the physical system shown as a plane embedded in the institutional sphere. And we're concerned here not only with the physical complexity, say, of the Mexico City transportation system, but also the institutional complexity of, for example, the interactions between environmental and transportation organizations, making actual control in any sense of that physical system all the more difficult. And both evaluative complexity and nested complexity are characteristic of socio-technical systems, and we're quite concerned about those. So relating to those ideas, relating particularly to the nested complexity idea, I cite, of course, one of the fathers of the field of complex socio-technical systems, Herbert A. Simon, an extraordinary individual on any number of dimensions. And in a paper of his, he talked about the idea of people making so-called rational choices that are input to some system, and the system performs, where the technocrats may not agree with the people about what rational really means. So rationally, people should take public transportation. Irrationally, the transportation folks throw up their hands and say, why don't they do it? It's an obvious choice. Well, people who are not doing it obviously have different dimensions on rationality. So this is yet another complication. Individual human beings making choices that may not be in accord with the way that we technocrats defined the system, designed the system, and hence the performance may not be all that we would expect. So let me try and talk a little bit about a structure for all of this to give you a sense of where I am going. Excuse me. So across the top, we label this an approach to the study of complex socio-technical systems. I'm hopefully by the end of this talk going to convince you that there is indeed a field of study called complex socio-technical systems. And I would argue this is one graphic that gives a perspective on how one might go about studying it. So we have in the middle of the chart integrative domain knowledge. In my case, I'm a transportation person. I would argue for me to study it as a complex socio-technical system, I've got to not only understand the nuts and bolts of the transportation system, but also understand how it relates to other domains, the environment, the economy, and what have you. So integrative domain knowledge of a particular domain, I'm going to suggest, is not that easy to come by, but it's very important that one has to study these systems in an effective way. So off to the left-hand side, I have something called systems-oriented methods that relate to the way in which we're going to study that integrative domain. So we've got, for example, optimization, the study of stochastic systems, system architecting, simulation, system dynamics, agent-based modeling, connection science, and so forth. These are all systems ideas that I can relate to my domain. And on the right-hand side, I have social sciences, management, and planning, which would include, for example, such things as economics, sociology, political science, history, strategy, organizational behavior, enterprises, finance, and so forth. So that's kind of the horizontal piece of this, integrative domain knowledge together with systems-oriented methods and with social science management and planning. But in addition, and importantly, we have shown vertically deep quantitative engineering science. So for the last 50 or 60 years, we spent a lot of time developing a lot of knowledge in deep quantitative engineering science. And this is extremely valuable. And in fact, is part of our solution set, part of our approach to complex socio-technical systems. It's part of the entire picture. So I'm going to suggest there's another step that we're going to go beyond the study of complex socio-technical systems to the design of socio-technical systems. Now we are thinking about actual system improvement. So I argue that those of us interested in complex socio-technical systems are not simply observers of the system. We're not simply trying to understand how it works and perhaps predict how it might work under other circumstances. We're talking about systems that are purposeful. They have some goal that they are attempting to achieve. So when we go into thinking about design, we go beyond merely observing and representing the system. Now we're talking about having a normative point of view. We have to ask the question, what does good performance actually mean? And in the context of evaluative complexity, what it means may be very difficult to understand, given the views of different stakeholders. Then beyond the normative view, we have a prescriptive view. How do we make our system perform better? Now we've decided what better performance means. How do we actually make that happen? So that's the work that we do, I would argue, within this field. And this simply is the same diagram, except I've replaced the word study with design, an approach to the design of complex socio-technical systems. Okay, so that's where we are. So now I'm going to start to try and build an edifice that will give you a sense of whether complex socio-technical systems is indeed a field of study. So let me set up my quote-unquote proof. We have an integrated view of a domain. That's a domain like transportation and energy. I've chosen two that are related, but these are just examples. And then I have the integration of various methodologies, also as part and parcel of what my diagram suggested. So we're integrating systems-oriented methods with social science management and planning and engineering science results. And we ask the question, is there any intellectual content to that action of integrating? That would seem to me to be important for a field of study. So I think about that a little bit, excuse me, and I decided the best way to try and demonstrate this is through an example. In fact, I've already mentioned it. About 10 years ago, I worked on a team with Mario Molina in Mexico City, looking at issues of the environment, and my particular piece of it was transportation and the environment. So Mexico City is, of course, one of the largest megacities in the world. It's the economic engine of our neighbor to the south, Mexico. I don't think I'm going to have to convince anyone who's been there that it has severe mobility problems, and those imply productivity problems, which given the economic engine aspect of the city is important. Those transportation systems have important technological aspects. We have complex vehicles, complex control systems, and the like. There are associated with the transportation system severe environmental problems with health effects. Air quality gets bad, and young people and old people start getting quite ill and maybe even expiring. We've got social equity issues. There's an enormous disparity in wealth around this city and, in fact, in the country. And the institutional sphere, the organizations that purport to control this complex socio-technical system, is complex indeed, and sometimes quite dysfunctional. For example, the interaction between transportation and environmental agencies in Mexico City sometimes leaves something to be desired. So approaching the question of what one can do to enhance the environment within the transportation area is indeed quite complex. And I would argue that indeed it takes a fair amount of intellectual energy, a fair amount of knowledge to be able to begin to make some headway on this particular complex socio-technical system. So that's my first element of the quote proof. I would argue there would be little question that there is intellectual content in integrating when one considers problems of the scale and complexity of Mexico City. And in the interest of time, I will present it as obvious. But to pass the test of field of study, I think there's a more important question that we have to ask. Are there principles and core underlying concepts for creating this integrated approach across domains? If we're going to look at education in the United States or the developing world, if we're going to look at the building of a pipeline from Canada down to Texas to transport particularly dirty oil, are there things that in studying Mexico City are in some sense transferable to studying in these other cases? Is there transferable residue? And I would argue that's a harder test to pass, to actually say there are things that that can transfer across those boundaries. So I've given some thought to this, and I'm guessing that others here have as well, and I don't suggest by any means that I have all the answers, but there are, I think, some principles and some core underlying concepts that can form the basis for the field of study. So this is a work in progress, principles and concepts. So one I start with, one of my favorites, is the whole micro-macro question. How does one decide how deeply one has to drill within some other discipline in order to make reasonable statements about how the system will behave at the macro level? And I'd argue there's strong intellectual content in understanding how to do that. Another principle that one might talk about is taking the enterprise view, a very broad-based, integrated organizational view. People like Debbie Nightingale, for example, have worked on that within ESD. Another idea is that of life cycle properties. We have to worry not only about the immediate behavior of this socio-technical system, but we've got to worry about its life cycle and how it performs. And Joel Moses has been talking for years about the idea of the so-called ilities as ways of reflecting that life cycle performance. And one of the ilities we worry about is flexibility, and it's the related question of resilience. So people like Yossi Sheffi, David Simke-Levy, Richard de Neufville think a lot about those kinds of questions. Sustainability as an overarching design principle for these complex socio-technical systems. That's, I often argue, is the most important ility of all, sustainability. So the idea of economic development, environmental protection, and social equity, the 3 E's, are ideas that I've thought a lot about. So has Frank Field in TPP, Chris Zegras in Urban Studies and Planning. I think that's a very important part of the intellectual edifice that we're trying to build. We've got more. So the idea of being able to use qualitative and quantitative methods rigorously, and there is such a thing as rigor when one talks about qualitative methods. Talk to David Mendel about rigor in the study of history, you'll understand what I mean. But here we need to do it in tandem. That is, the representations and models can't be disconnected. We have to use qualitative and quantitative methods together and in a rigorous fashion. So people like Ken Oy, for example, in political science, worries about this kind of an idea. One of my own personal favorites, in the kinds of systems that we worry about, we need to focus on feasibility. We need to focus on what we can get done. We need to focus on satisficing, not necessarily optimizing. In most of the systems that we're concerned about, optimality is just beyond the pale. It's beyond our grasp. Coming up with a few feasible solutions may be all we can expect to accomplish. Understanding and measuring complexity in a socio-technical context. People like Ali Dweck have thought a lot about this question. What does complexity mean in this context, and how does one measure it? Using system architecting as an organizing principle. Any number of people have been concerned about that. In ESD, Warren Searing, Chris McGee, several others. I'm terrified I'm going to leave out someone's name. Don't take it personally. It's my failing, not yours. And finally, the idea of identifying and quantifying uncertainty and creating strategies for dealing with them. And people like Richard Denoufel, David Geltner, Dick Larson, Dan Fry, all of them have thought a lot about uncertainty on different dimensions and how one creates ways of trying to ameliorate those irreducible uncertainties. Recognizing system safety as an emergent property of a complex socio-technical system. Nancy Levison is the recognized leader in this whole area of endeavor. Recognizing the importance of context in understanding the performance of a complex socio-technical system. My good colleague Dan Roos has talked about context as a vital piece of the puzzle. And it's interesting as I look at these last three bullets that these thoughts are all represented in the recent MIT Press book series dealing with engineering systems and how we're going to in fact advance the field of study. We have Denoufel working on uncertainties and flexibility, system safety, the most recent in the series by Nancy Levison, and Dweck, Roos, and McGee, the flagship book on defining the field of engineering systems. So I'd argue that the very presence of that series is an important foundation for complex socio-technical systems as a field of study. So we've gone beyond, I hope, the idea of complex socio-technical systems in a particular application, Mexico City, as I used as an example. We've gone beyond that to begin to establish some general principles and concepts. And I would argue that in order to claim field of study status, we're going to have to continue to do that, and to do that with some effectiveness. So many of you know I'm a Peter Drucker fan I'm the president of his fan club, the late Peter Drucker, the management sage. And whenever I have a talk to give, I go to this extraordinary file I've collected of his quotes that are almost invariably of value. So he says here, only connect, in quotes, was the constant admonition of the great English novelist E.M. Forster. And what Drucker says is the ability to connect, thus to raise the yield of existing knowledge, is learnable. It requires a methodology for problem definition. It requires systematic analysis of the kind of knowledge and information a given problem requires, and a methodology for organizing the stages in which a given problem can be tackled. The methodology that underlines what we now call, quote, the systems approach. To make knowledge productive, says Drucker, we will have to learn how to connect. So I would present that as another element in our case for building a field of study. Now, complex socio-technical systems didn't appear instantaneously, spring from the brow of Zeus, so to speak. That's not Roos, it's Zeus, I said. But it didn't fall from the sky. I mean, we all of a sudden didn't wake up and we said we have complex socio-technical systems. There's a significant history with distinguished progenitors of this field, and people like the aforementioned Herbert Simon, Norbert Wiener, J. Forrester, Schumpeter, von Neumann. These are all people who laid, in many ways, the important foundations of what came to be, and indeed in ESD 83, which, whoops, something happened. Oh. Good, thank you. Did I bump something? It's possible. An unintended side effect, we call that. In ESD 83, which is the doctoral seminar for all incoming ESD PhD students, which Chris McGee and I have taught for the last several years, we have embedded within it a history assignment, and we call it the historical roots assignment. We give the students a list of the historical roots of the field and also a list of the current day methodologies that we think are part of our study of complex socio-technical systems, and ask them to trace from one end to the other and back. And actually, we wrote a paper about it for the CSUN conference coming up in Delft in a couple of months. And it's the students argue a terrific educational exercise, basically not arguing we're all brand new, but arguing we are descended from many distinguished folks. Now, one of the ideas that has some historical resonance, I picked this up from a paper called Science and Complexity by a fellow named Warren Weaver, written many years ago, written perhaps in the 1960s, if I recall, who talks about the importance of interdisciplinary studies in the context of some of the extraordinary work done during World War II by interdisciplinary teams that came up with some remarkable insights in the context of the war effort and how we should and how those different disciplines fit together to produce something that couldn't have been done with only one or two. But it was interesting that when the war ended and one had now this bag of tricks that had come out of the war, it was in many ways some of the basis of fields like operations research and systems analysis. When one indeed began to try to apply that, the RAND Corporation was one organization that tried it in social settings, in a socio-technical context, as opposed to a war context where your figures of merit are pretty clear. Things didn't work so well. And in fact, it probably set the field back for a decade or two while people recognized that one had to worry about the human and sociological aspects of the solutions that were produced. The same lesson I learned on the railroads back in the late 1960s and 1970s. Now, I've mentioned J. Forrester as one of the progenitors of the field, and I went to I own a book, I should say, called The Collected Papers of J.W. Forrester, and it's got some exceptional papers about urban dynamics and industrial dynamics and so on and so forth. And what was interesting to me, in addition to the substance of the papers, was the foreword that was written by one Dean Gordon Brown, who Dan mentioned as the person who appointed Charlie Miller back in 1962. So Brown says, among other things, this book might appropriately be titled Seeking to Understand Today's Complex Society, rather than Collected Papers. And he says pretty much what Lady Bird Johnson said. Stated succinctly, we live in a world where everything affects everything else, and goes on to talk about scholars in many disciplines having addressed themselves to these dilemmas, these complex issues, The disciplines of OR, econometrics, behavioral science, statistics have been developed and applied, but our problems escalate, and we need to come up with more new and more powerful approaches. They're urgently needed, Brown says. And he goes on, there's more to the quote. He speaks about the industrial establishment, the legal establishment, and so on, and how one has to worry about the dynamics between them in order to really make headway. And it seemed to me, as I read what Brown had to say, that he was talking about a field like complex socio-technical systems, one that connects these different disciplines, these different bodies of knowledge to solve the kinds of issues that we're interested in. So I found this particularly interesting because Gordon Brown was the Dean of Engineering, who is widely credited with the major and positive initiative to create engineering science as the frame of reference in the School of Engineering at MIT, and in fact, as it happens now, more and more around the world. So here's Gordon Brown, the giant of engineering science, and a giant he was, and a giant administrator in terms of making things happen. And here he is in the mid-70s saying, that isn't enough. He's saying, we really need, if you will, to use my terminology, a more horizontal approach as well. We need, in addition to the deep engineering science that we have developed, we need an approach that allows us to look at complex socio-technical systems. So the juxtaposition of Forrester and Brown in this particular way is quite interesting to me. So why now? Why am I up here today as opposed to 10 years ago or 10 years from now talking about this issue? People have talked for decades about cutting across disciplines to study complex socio-technical systems. Why is it especially important as we sit here in 2012? Well, I've got several responses. I think it's a question both of supply and demand, if you will, as I reach back to my transportation roots. Critical contemporary issues that we frame as complex socio-technical systems are widespread. They're endemic and can only grow in importance. They're not going away. They're going to get harder and harder to solve. So there is an ample demand for our abilities to study these systems more effectively. And the second is a question of supply. The second bullet, we now have the tools, the technologies, principles, and concepts to work effectively across disciplines. So we've got both those conditions in place. It doesn't help to know that agent-based modeling might be a terrific technique if you don't have the computer capability to actually work on those kinds of models. It doesn't help to think about system dynamics as a terrific tool for representing systems, unless one has the software to address it, and one could go on. So supply and demand makes this the right time. Some of you may have noted that I've basically not used the word engineering systems for 45 minutes, and everybody who knows me knows if you shake me wide awake at 3 o'clock in the morning, the first words out of my mouth would be engineering systems, and I haven't said it. And the reason I haven't said it is that I say here by our definition, I really should have more fairly said by my definition, engineering systems are in fact complex socio-technical systems. There's an equivalence between them as I see it. Again, we may have differences among colleagues about whether that's indeed correct, but my view is that is the stamp, that is the brand, if you will, of engineering systems, that it is a study of complex socio-technical systems. They're concerned with technologically enabled networks, They transport mass, energy, information. They're large scale. They have socio-technical aspects. They have the nested complexity I've talked about. They are dynamic. Time scales are important. And they require deeply rigorous quantitative and qualitative approaches performed in tandem. So that's what I think we are about here. And as I talk about the future of engineering systems, and now I'm saying engineering systems / complex socio-technical systems, they are identical. We address critical contemporary issues using the engineering systems, complex socio-technical systems worldview. That's what we do. And I argue that we here at MIT importantly need to create value for society by studying these kinds of problems. The integrated interdisciplinary approach is a pathway for relevance of universities, and now in bold, in a society where relevance is demanded by all institutions. We can't simply sit in our ivory tower and say, well, eventually what we're doing is going to have some value. I think the world is properly demanding of us that we have relevance in the nearer term future. And kind of the punchline is only by considering engineering systems / complex socio-technical systems as a field of study with some basic principles and concepts underpinning it, can we make a continuing contribution to critical contemporary issues. We can't simply do Mexico City, figure out how to create that integrated framework, forget about it, here comes the next problem, let's build it up again. I don't think that that is particularly effective or efficient. And if MIT and if the world is going to really get traction in studying these critical contemporary issues, creating a field of study that retains that value from project to project is extraordinarily important. So I will stop at this point. I thank you for your attention and would be happy to try to take some questions or comments. Thank you. Professor, go ahead.
Joe, I have a
It's on. Yeah.
good a question about your notion of residual knowledge.
Yeah.
When we solve a problem, there should be something that generalizes to other problems.
Right.
In my other home department of mechanical engineering, we have people who go so deeply into problems that nothing they find would ever generalize, and we celebrate that. Mm-hmm. You're saying that if you only solve the transportation problem in Mexico City and nothing generalizes to London or Tokyo, then somehow you failed. Why do you set the bar so high?
For the field of study idea. Because the notion here is, in order to be able to progress along these important dimensions, simply solving these problems as one-ofs and then going on to a totally different approach for a different problem seems to me to be wasteful and also, in some sense, intellectually unsound. That is, our goal should be to create that kind of value, that kind of residual, to allow people up the road to build upon it to address problems in a more effective and more efficient manner. Drilling down very deeply is a different approach. I would imagine that some of the techniques, some of the ideas that the engineering scientists come up with as they drill down would in fact be transferable to another engineering science application, some of the mathematical treatments, whatever they may be. So I'm not sure I accept your argument that there isn't any residual in the vertical engineering science perspective.
Thank you. You said something which was particularly intriguing to me during your talk, which was...
Just one thing?
Well, one thing especially intriguing. And you'll know what it is in a second. It had to do with, you said, what you learned when you were working for the railroads in the 60s and 70s.
Right.
So what did you learn when you were working for the railroads, and how did you learn it?
Well, I was alluding specifically to the fact that we came up, Chef Lang working with me, Carl Martlin's in the audience. He was part of this team. We came up with some ways at looking at the way railroads provide service and how they could provide it in such a way that their customer base might react more positively, and we might be able to interrupt the shift from rail to truck. And I'll have to give you a little railroad background, but the holy grail, the essence of railroading is run long trains. Because if you run long trains, the marginal cost of the 101st train on a 100-car train is tiny, so you can do it virtually for free. So that's true, but what's also true is the way you run long trains is you run infrequent trains. That is, you have to wait for traffic to build. The 100 cars don't necessarily appear every 12 or every 24 hours. So the work we did looked at the cost functions associated with running railroads, considering the real value of rolling stock, and said, you know, you've got a lot of assets that are hanging around here, not making any money for you, because you're worrying about, because you want to be sure you can add that 101st car and do so very cheaply. So that was the essence of the research. But then going out to the Santa Fe and going out in those days to the Boston and Maine and the Southern Pacific, great names, many of which are no longer among us in the rail industry, and saying, here is the way you really ought to be doing this. There's, you know, there's a new way of thinking about these problems, and often encountering a stone wall. That isn't very useful advice in the culture that people have been brought up with, that emanated from a period in which truck transportation wasn't really a competitive element. I mean, this is thinking that went back to the 1930s, so to speak. So what I learned was that one had to be able to package results, and one had to be prepared to convince people, even when it was well outside of their cultural field of view. The same kind of thing with ITS and the Massachusetts Highway Department. People earned their spurs by building and maintaining highways. They don't want to hear about new technology. Let's use the infrastructure we already have more effectively. Why would I want to do that? You know, I like to build highways. So one has to recognize when one creates what we think is value based on technology and mathematical analysis, one has to understand the context in which one is embedding it, and it's not always easy to do.
Joe?
Ollie back there.
Yes,
Ollie.
so following up on that question with the railroads, it seems that many of the systems you mentioned weren't designed based on a single master plan and have very homogeneous. Many systems, like the railroad system in this country, and perhaps the electrical grid, formed through a process of coalescence, where you had, say, local or regional systems that were owned by particular organizations and implementing their own, their own views, according to their own objectives, and then over time coalesced more or less gracefully into these more aggregated systems that had very homogeneous technical specifications, but also distributed ownership. And now you didn't mention a system of systems, but it seems that if we look across, the electrical grid, transportation, water systems, and so forth, that one of the major challenges in getting, I want to say optimality, but higher levels of efficiency is that we're in fact dealing with a very stitched together set of systems. And so do you view this as one of the major challenges of the field, and how does that relate to collaborative systems or system of systems?
So that's quite a good question. Many of these systems have evolved into what we have now. We deal with the question of legacy systems. We have trillions of dollars invested in them, And while we might have a better idea today, that doesn't necessarily mean we can write off those trillions of dollars. So yes, I would put that directly. Maybe we will add that to the list of concepts and principles, the idea of needing to learn to deal with legacy evolutionary systems. I think it's an excellent point. We got a...
This is a very interesting room for you to have given this talk. You're in the heart of ECS land. So let me tell you how many of the people you mentioned are actually represented by these photographs. If you look at the top left one, the person on the left is easily recognized.
That's Norbert Wiener.
It's Norbert Wiener. Who's the
Yes.
guy in the middle?
That's Jerry Wiesner.
That's Jerry Wiesner. Well, the guy on the right is Lan Chu. I wouldn't expect you to know that. That's probably around 1950. The middle photograph, the larger one, the person on the left is the most important person in determining university policy.
Vannevar Bush. Right, okay,
exactly. And I can date that exactly. That's May of 1928 because this building is named after Egerton, Germershausen, and Greer. This is the Greer room. And Germershausen and Greer were Doc Egerton's students, and they formed a company called EG&G. That photograph is of, according to Egerton, of his master's thesis. And he was standing on the side telling people, don't touch anything. Now, the bottom right photo, the person sitting on the left is someone you mentioned several times. That's Gordon Brown, working on his version of Vannevar Bush's type of analog computers.
So you know these pictures by heart. Surely you don't see that from where you're standing, right?
I do.
Thank you, Joel. That's a very apt comment. I did, by the way, get a safe conduct pass before coming into EECS territory.
Professor Sussman, you mentioned about designing under uncertainty. How about conditions where there are unknown unknowns?
How about them?
Do you have an opinion on designing and?
These are exceptionally difficult problems and unknown unknowns. One, I tell my students, you can't give an example of an unknown unknown, because if you could give an example, then it's not an unknown unknown anymore. So it goes to the question, I think, of the ideas of flexibility. People like Richard Denoufel have pushed it to hedge against these uncertain futures, not only uncertainties in things we know about, like uncertain demand, for example, which everyone understands, but things we may not be able to foresee at all. So the idea of building flexibility in at some hopefully relatively modest cost to be able to make a decision 10 years hence that will be closer to optimum is, in fact, I think, the way one thinks about it. So in our research in high-speed rail, some of my students are here. We've been studying high-speed rail in the Northeast Corridor and in Portugal and in Japan. One of the things that we've been working on to try and shed some new light on high-speed rail in the Northeast Corridor, which, as I mentioned earlier on, has been going on for a long time in terms of nothing happening and gridlock, if you will, is how one builds organizational flexibility. We don't, if high-speed rail does roll out in the Northeast Corridor, it's very unclear how exactly it will happen. What will be the role of Amtrak? What will be the role of the private sector? What will be the role of the connecting commuter railroads, and so on and so forth? So we've looked at the real option, if you will, the flexibility of building some organizational wiggle room at time equals 0. So in 5 years, depending upon how the future works out, we have an easier path to what would be an effective an effective organizational structure. So I think there's no answer to the question, but I think building flexibility, paying a modest price up front to have flexibility in the future. Of course, if it turns out not to be useful, well, the whatever monies you spent will disappear. But oftentimes it's well worth the expenditure.
All right, I just have, I thought it was a great talk, by the way. I'm actually a sociologist, so I take a
I told
slightly
you I was
different-
going to say sociology.
Yes, you did.
He was trying to confuse me before the talk, giving me all sorts of sociological stuff. I said, please stop.
Well, what's fascinating about your call for a new field is that the concepts you listed, as far as I can tell, are deep in the core of the epistemology of sociology. The micro-macro problem has been addressed by sociologists. The notion of context, satisficing even as opposed to optimizing. So there might be a branding issue slightly. However, sociologists, it was much more popular in the 50s and 60s, this sort of systems thinking, but it's declined with methods of data analysis, where it's only now becoming more widely available that we have systemically available data. So that's one issue. The second thing is that it seems to me that the main approach to socio-technical systems that is in opposite of what you're proposing is mainstream economics today, where supply and demand models are linear rather than nonlinear. People are assumed to optimize rather than satisfice. There's one prescription, one sort of policy prescription. So maybe you can address the policy and sort of the implications of this approach for actually forming policy. So those are my
Okay,
two
well,
comments.
thank you. Those are some interesting questions. Your comment that it relates to the core of sociology is particularly interesting to me. I wouldn't have known that a priori, but now that I think of it, it makes a certain amount of sense. The difference, of course, is that when we talk about technological, socio-technical, not simply social systems, we get into a field of view in which sociologists will have to, in some ways, integrate and work together with technologists, and that's a big step. As the doctoral students from ESD know, we require a qualitative methods based on sociological concepts and others for the doctoral program. So we've kind of gone our step, getting the sociologists to step in our direction may be more difficult. The economists are a different breed altogether. They live and die on mathematical elegance and don't worry a whole lot about what it predicts. That's a little harsh, but not completely so. I think they now understand that nonlinear is different than linear, and linearizing, just because you can do the math, is probably not that great an idea if you want to predict what will actually happen. And you're starting to see, with the field of behavioral economics, you're starting to see the economics profession recognize they're dealing with people who are making choices that are rational in their minds, not in the minds of the economics professorate. So I see progress there, but there's a ways to go.
Let me ask you a question. You argue, and I agree with you, that it isn't sufficient just to be able to do Mexico City with a series of approaches, that those approaches have to apply to many, many different problems. But I would suggest that finding what the approaches are isn't necessarily sitting down and just thinking it through, that every time we solve a large-scale complex problem, that it gives us insight in terms of what those generalizable principles are. Mm-hmm. So in a sense, it's not just the theoretical study beforehand, but it's learning from the problem solving that we're doing.
Yeah, I agree with you. I agree with you totally. When I used the term residue, that was at least part of what I had in mind. The fact that you'd have something methodological left over that then could be applied to the next set of problems. And keeping a faculty together that continues to accrete this knowledge as more and more critical contemporary issues arise, that the knowledge accretes like coal being built up in a coal bed. That's I think the key to the long-term success of complex socio-technical systems as a field.
We'll take one more question.
We had one over here. Sorry.
Eric.
Oh, no.
Oh. Uh-oh, I prefer Eric, actually.
Joe, you talk about a new field of study, and I'm wondering if you'd like to comment on what level this is, because I'm sure you would have ideas that you could express to a group of high school students interested in engineering, or undergrads, or master's students, or PhDs, or a group of, like we have in this room, of people with kind of vast experience who might be interested in affecting policy.
What level from a hierarchical point of view?
If this is a new field, who is going to be learning it, and who is, I mean, is this for PhD students, or is this something that would be a class for everyone at MIT to take?
No, I understand. I think the building of the new field of study is a graduate and faculty kind of a process. That the level that's represented for the most part in this room is probably the right level. But that's not to say that it can't be directed to, for example, undergraduates, as we try and do in classes like ESD 00, or that you and I try to do in Course 1, in 1011. So I think the intellectual foundation comes at this level, but I think moving up the chain to make a more sophisticated set of concepts and principles is appropriate as doctoral students think more deeply about this. And moving down the chain for, say, undergraduates, and I guess plausibly at some point some kids in high school could benefit from this kind of thinking as well. We talk a lot about the educational strategy of when you introduce this kind of material. And many of the departments in the School of Engineering will say, this is good stuff, this is important stuff, but it shouldn't be addressed until we get to the graduate level. That first a student has to be grounded in a vertical sense, and then when they're 23 years old, 24 years old, then we can expose them to these cross-cutting themes. And I worry about that somewhat, because I think that many students, freshmen, come to MIT with a kind of change the world kind of an attitude. They're all, full of piss and vinegar, so to speak, and they're really ready to work on climate change. They're really ready to work on mobility. But instead what MIT says is, well, yeah, that's okay someday, but first let's put you in these silos, and let's make sure you can do the math and do the chemistry and do the physics. So by Thanksgiving, they go home discouraged, and they say, well, I guess I'm going to have to wait a while. And I worry a lot about that once we force them into a reductionist perspective, it's going to be very hard for us to win them back later on, because they become convinced that's the wave of the future. I'll take one from Eric, too. I mean,
Thank you.
I hope this is a softball one.
This is definitely a softball question. It seems that if you look at the evolution of fields of knowledge and fields of study, that they take place over a number of years, and there are central elements that bring them together. I would argue that even though MIT might be necessary, it might not be sufficient to get a field going. So, if not MIT, then who else to start a journal on complex socio-technical systems, where you can actually accumulate residual knowledge, methods, and a community identity to develop a field. Because these problems are, if we believe they're multidisciplinary in nature, that you have to have sociologists and engineers economists and who knows who else involved in solving these problems, there has to be some way for them to advance in their respective careers, for them to invest the kind of energy and intellectual creativity into solving these kinds of complex problems.
These are important questions. I think MIT is in fact a hotbed for doing this, but certainly we shouldn't and couldn't be alone in advancing these kinds of ideas. Peer institutions, Berkeley, Stanford, Texas, all sorts of places. I think one has to be able to reach out and create a web that will advance the field. I'm reminded of a joke about what's the difference between a political scientist that works with ESD and one that doesn't, and the answer is the one that doesn't got tenure. So we have a lot of that to overcome in order to create what I'm suggesting we create. Okay.
Just to follow that up, Eric, a little bit after ESD was created, we had a meeting where we invited the heads of similar programs from the top universities to come and meet. And two things were very interesting. The first was almost no one in the room knew anyone else in the room, so there wasn't a community. And secondly, if you looked at the names of each of the programs, no two programs had the same name. So, you know, if you go to Berkeley, it's what? Engineering, management.
Yeah.
And some have system engineering, all types of different names. So in a sense, there's a branding problem, and what we've been trying to do, we created an organization called the Council of Engineering Systems Universities, which now has about 50 members, and Ali Dweck is the representative here at MIT, and that organization meets yearly with the idea that collectively we have to work in terms of developing this field. Joe, I want to thank you for really terrific talk. I think you have energized and encouraged everybody in this room now to go the next step, having convinced them that there really is the basis for this being a not only field of study, but a really critical field of study. As a small remembrance, your talk.
This is a large-scale version of what you've been staring about at off every bulletin board at the Institute for the last 2 weeks. Even I'm tired of looking at it.
So thank you very much for a wonderful talk.
And thank you for coming.